Hello, so today I'm going to build a power bank in the EasyEDA software. It's the circuit that will charge the battery and discharge it and deliver us 5 volts on a USB output. I'm trying to use all basic parts, so if you like to get it assembled, it will be very cheap with JLCPCB's assembly service. And this video is not sponsored in any way. It's just that I think EasyEDA is a good and easy design tool to get started and even do professional work on PCBs. So if you think about a power bank, there are two basic parts we have to keep in mind. There's one part that charges the battery and one part that discharges the battery. For now, I'm not going to take into account battery protection. That means that every cell you attach has to have a battery protection circuit on it. All cells have to be protected and safe, and to be safe. I will not be liable for anything that happens. If you do something wrong or do it right and something goes wrong, this is just for the technical part. So if we start off with the battery charging circuit, there is a basic part that we can use. It's usually a TP4056. It's on most lithium charger boards. You can see that here. That's an SOIC8 package, and this IC takes care of the charging of the battery. There's another thing we need for that, or we should use, and that's an LED. This IC is made to use two different LEDs. One, while the battery is charging, it lights up, and the other one lights up when the battery is finished charging. So if we look here, we will have to see look for an LED which is basic. We have to get one LED which is red and one LED which is green. So if we look here, this is a green LED. It's 0805 package. It would be nice to get another basic part where the LED is red. Well, this is out of stock. Let's just do some search and find out where we can get the best LED. If we open this LED in a web browser, if we click on their number, we can see, okay, it doesn't show us anything about the color. That's not so nice. Also, it's discontinued. So let's just go ahead and see if there's any part that is in stock right now. This one seems to be in stock. 0805 LED. Which color does it have? Red. Okay, so this will be our red LED. And then we have to get a green LED, which is hopefully also in stock. There is none. Okay. Let's just take this 0805 LED and hope that works. Okay, so now we have the two LEDs. Also, we need capacitors. And a basic capacitor, which is very good to use in most projects, is the 22 microfarad Samsung capacitor. It's 0805 package, and it is 25 volt capable. It's out of stock right now, but it will be in stock soon. I use this port in many designs, and I'm very pleased with the outcome. It's X5R, but that's good enough for our purpose here. We just use it as a bypass filtering capacitor on the input and output. So one will be in parallel to the battery, and one will be in parallel to the input. And to make the power bank design complete, we will use a micro USB for charging. So for that, we go to LCSC and we type in USB. And we can then go here to connectors and USB connectors. And then we should be able to search for USB micro A, or let's just go ahead and make it USB Type C. Just search for price scanning. All of these connectors, they are not available to be assembled by JLCPCB for some reason. They don't do through-hole parts, and they also don't have connectors which are SMD only. I don't know why, but well, that's just how it is. But this connector seems to be easy to be soldered by hand. So you could just get most of the parts assembled by JLCPCB and then do the rest by yourself. We go here, we enter the number. We should get that here. And well, it doesn't show us the exact numbering. We will have to figure out what is positive and negative by using Google. Okay, so this will be our input, and also we need an output. So let's just go ahead and search for normal USB Type B. That's the normal USB out. No, is it Type A? No, I'm confused. Yeah, it should be Type A. This is our output, yes. Let's just go ahead and use a basic port like this. We need this number, we enter it here, and then we get our output. Also, there's something that we also need, which is like a connector for the battery. So we'll just go ahead here and search for female and male connector types. And then we should be able to find a normal 2-pin, 1-row. Well, it doesn't matter with the 2-pin, which way around it is. And we just get this part, copy that number, put it in here, and there's our battery connection. Another thing you need is an on-off switch, because, well, you have to turn the power bank on and off. So we just search for switch. It should be not a tactile switch, something like a slide switch. We'll have to see if it works with slide switches, if we can search for it. Well, that's relays now. We don't need a relay, we need a slide switch. Do they have something like that? Let's just go here, push button switches, and search for toggle switches. That's what they're called. And we should probably use one with a high current rating, because if we're able to find one, we can just pass the battery power to the output stage to it and be safe in any way. This one seems to be okay. It's 3 amp capable. That's all we need, and it's small, and the voltage is okay also. That looks good. So this is the battery. The battery charger is up there. This is the on-off switch that powers our boost converter, because we would need a stable 5-volt output. And a good converter is always the MT3608. This is not a basic part here, but it's a good IC. I use it in many designs and it just works. What we also need is an inductor. The MT3608 requires a 22 microhenry inductor. We can see that in a design down here, maybe. Do they have a typical application design? They do not, but they tell you here that the average should be 4.7 to 22 microhenry, and if you go with 22 microhenry, you're pretty safe that it runs more stable. Also, we need a resistor array for the feedback. We have to calculate this, because we need a feedback voltage of 0.6 volts while getting an output of around 5 volts. But as of for now, if we use a 1 kilo ohm and a 10 kilo ohm, we should be able to get 5.4 volt output, which is with the drop on the PCB. Totally in USB standard, it will be like 5.3 on the output with all resistances, and this is just in USB standard, and we just use that. So we search for a 10K resistor. I guess it's okay to use 0603. If we get it assembled, that's no problem. Soldering by hand can be hard for some people, but well, it should just work. And also we use a 1K on the enable pin to pull the enable pin high to supply voltage, so it turns on automatically once it's supplied with power. We also need power inductor. We can get that from EasyEDA, from LCSC. Where is it? Power inductors. Should be around 22 microhenry, and it should be 3 amp capable. That around the maximum that the MT3608 can switch. Let's just try to search for a 3 amp version. The output should be 1 to 1.5 amperes on the USB. But this one just looks nice. Let's hope they have it in design. Often they do not have inductors in their design for some reason, but well, this one they have. So yeah, let's just go ahead and build that thing up. This will be our feedback. This will be on our output side. And yeah, let's just ground everything. The shield can also be grounded. The entire PCB has a common ground topology. So we can go ahead and just ground everything. We just decide now that pin 2 is ground and pin 1 here is the battery. You can just go ahead and put that on the battery pin of the TP4056. That's our charging output. In parallel, we put, well, let's put 2 of these 22 microfarad capacitors, because when switching we might have some high current demands. We just use it as a bypass capacitor. And that's our filtering there. On the input, we just make another net, which is our USB. And we have another thing here, which is ground. The VUSB goes to BCC. Chip enable should also be pulled high. And the datasheet says that if we don't use a temperature probe, we can ground the temperature pin. And there's another resistor we need for programming, and this will be shorted to ground. Then we have 2 LEDs here. They should use 1 kilo ohm in series, and this entire thing uses open drain topology to drive the LED. So the positive of the LED should go to the USB voltage, input voltage. Now we just need to find out which programming resistor we have to choose to get our right current. We can go ahead and yeah, I would like to drive it at 1 ampere because that's just a lot. Let's just go ahead and drive it like at 800 milliamps or something they specified in their data sheet here. Our prog is 1.2 kilo ohm. Yeah, let's just go with 2 kilo ohm. That should be around 600, 700 milliamps. That will not make the part too hot. And the thing we can do here is to keep the bill of materials small. Let's just go ahead and put 2 1 kilo ohm resistors in series. And then ground that thing. EPAD should not be connected. That's stated in datasheet. You can look for that to make sure it's done right. This is our power switch. We switch the positive voltage. We leave the ground connected all the time. And we use this output as the switch. This will be the input of our converter here, and it will also enable it. We could, in fact, switch the enable pin, but because of the topology of a boost converter, if we do that, we have a problem, which is that this will just pass through with the internal diode, and by that it will lead to like 3 point something volts, or battery voltage minus 0.2 volts on the output of the USB, which is not good, because some devices will be semi-powered, which is just not, we should do that. Then we use this thing here as a feedback. Let's just use ground on a 1 kilo ohm, and we make another net, which is the output. This goes to BCC here. This V output also feeds the feedback loop 10 kilo ohm resistor. I just found out that we might also need a diode. We use the Schottky diode here, and we saved the project because it was not saved yet. We search here for diode, Schottky barrier diodes. Okay, we have some basic parts here. Let's just search for it. There's a basic part, yes. SS54. That's very good. It's a 5 amp, 40 volt rated Schottky diode. And I'll have to check the datasheet of the MT3608 again to find out what should be the topology. So we use VIN, and this connects to switch. Let's just go ahead and do that. We use V switched, and then we get the diode, I think, in this orientation. Yes, with the negative to the output. And this will be connected to the output, and just to get a stable output, we will just use 2 more of these capacitors in parallel as bypass capacitors for the output. Okay, I'm sorry for the loud keyboard. That's a mechanical keyboard. It can annoy people. Yes. We leave data minus, data plus open. We just assume the device can take some current. So let's just revive the design, revisit it, go over everything. This part should be finished so far. We have OV switched, which is also on the enable, it's on the input. There is an unconnected pin. The feedback gets it from the output here. This one is correctly attached. So our filter, well, okay, it seems to be good. We only have to find out about the USB pinout. I will just check that on Wikipedia. We're typing in Wikipedia USB Type C. And there we are. Showing the nice OnePlus cable there. A1 and A12 and B1 and B12 are both ground. So 12 is ground. Let's just go ahead. I'm not sure about 0. I guess it's the shielding that should also be grounded. It doesn't necessarily have to, because the device on the other side will also ground it, and we don't need a lot of shielding here because it's just there for power transfer on this line. So we can just leave it open. We don't have to ground it because I'm not sure if it really is the shell, and if it's not, we might end up making something wrong. So I just leave it open here. And what else do we need? We need A9 and A4 and B9, I guess. Yeah, it's V bus. A5 and B5. What's A5 and B5? A5 and B5. B5 is configuration channel for power, and A5 is also configuration channel for power. Okay, so we don't use that here because this would be assuming we'd use some special protocol, but no, we're not doing that. So let's just go ahead, ask the design manager to check our nets. 1 pin of the switch is not connected, that's okay. Pin 9 of the charging IC is not connected, that's okay. Pin 6 of the booster is not connected, and we do not have connected the USB 1, pin 3, 4, well, that's okay. And USB 2, we don't have the data pins connected. Yeah, what is U4? Where does that go? Does it show me? I don't know. Okay, then we just leave it here. So yeah, that is the power bank circuit. It's done. Very nice. Yeah, you can just go ahead, convert it to a PCB, lay it out, and there you have your power bank. It will charge a battery at around 600 to 700 milliamps. And yeah, it will output around 1 to 1.5 ampere under 5 volts and just run perfectly fine. There's one more thing I have to check. The green LED is for standby, but it's inverted standby. But that should be okay. Let's just check in the datasheet if the red and green LED is connected correctly, because it might be mixed up. And yeah, standby uses LED whatever. I cannot decipher that. So I'm just gonna check with another datasheet, TP4056 PDF on Google, and that shows you this thing here where it says The green LED is on the standby pin, and we just have it the same way here, the red LED on the charge pin. So it will light up red when it's charging and light up green once it's finished. Well, and I just went ahead and asked myself, I show you the entire procedure, so let's just go ahead. Go to convert to PCB. No, don't check nets because we checked it ourselves and some things are just not connected. And now we have the entire thing here. And go ahead, lay it out. If you zoom in, you can see the exact nets. I'll make it in a way that we have all the I/O on one side. Switch is there, the USB is there. Let's make it a logical order. We put power in, and we can turn on or off to put power out. Yeah, we can increase the PCB size here a little bit. Yep. Then you just place the parts where you think it makes sense to place them. Well, it makes sense to put the bypass capacitors for the V input close to the input, for the V bat close to the battery, and for the output close to the battery. This is for USB, this is for the battery. Let's just go ahead and put that USB thing there. Just press R to change it, but change the orientation, but we see it doesn't really make sense to change it because, well, it's like interwoven in USB Type C. Yeah, there are two more LEDs with resistors for them. Just multi-select them by keeping Control pressed and hopefully not moving the label, but the LED themselves. Okay, put it somewhere here, close to the side, so it's easy to see it once you make like a package for them. See if the routing makes sense. Nope, we mixed up the upper and lower one because once we let it route, it should make more sense to put the LED, which is connected to the most lower pin, on top because the routing just works easier then. For the output here, we use our two output filtering capacitors, put them close to the USB. This is our battery filter, and we can just go ahead and use this battery pin here, and we rename it, and we name it minus battery plus, so we know that this is negative, this is battery plus on the screen. Yes, put it somewhere here close to the switch where we need the entire thing, close to the battery charger. Well, that makes not too much sense to put it this way. Let's just see. Once we turn that thing and this thing and this thing, it will somehow be able to still connect. Just to make sure that the routing is somewhat useful and senseful. Okay, we have to place the inductor somewhere where there's a lot of space, so let's just move that down a bit. Let's put the inductor here with the switching IC close to it, just for EMF reasons. What else do we have? We have these two things that form the feedback loop, I guess. No, this one forms the feedback loop. It's the resistor divider, and this one is the resistor that does the enabling of the IC. And we use this one for feedback. Yeah, that should make sense, somewhat like that. Yes, okay. And what do we use this for? Why do we have those resistors again? What's their purpose? I can't remember. Why did we put them in there? Let's just go back to the schematic. It's resistor 6 and 7. What do they do? Oh, it's for setting up the charge current of the charger IC, so they belong up there. I see they're both in series, so let's just put them in series in the design and hope it somehow fits on a PCB. Well, that makes a little bit more sense now. Now, space-wise, it all works. We didn't put an LED in there to indicate the output is okay. So let's just use a white LED. Why not use a white LED? Because that's just a different color, and why don't we get any basic parts anymore? What has happened? White SMD LED. Yep. Let's just put that here. Well, it doesn't keep the bill of materials low, but you can just change it with your desire. Use a 1 kilo ohm on the positive, and then use the output voltage and ground to power it. This will give us information if the 5 volt or the output is there. It will also light up at around 3 volt, but well, we have to live with that. Now we can update the PCB, but we should save it first. It's now saved, and now we can also update it. Go ahead, update it. Keep on going. We checked the net so far. Keep the settings, and let's just go ahead and where do we put this LED? On the side, close to the output, just so that it makes sense somewhat. Let's just put that there. Nice. So the PCB actually is not very big. Let's just put it that way. It's actually quite small. Yeah. Pressed. We can just go ahead and measure it in a second. Yeah, that should work. Let's go here and put it to millimeters. Press N and start measuring. So that's 28 times 44 millimeters. That's not too big. Go back to mil because I like to use the autorouter with mil. I just learned to use mil. Let's go ahead and use about 30 mil. Try to route it on the cloud. 30 mil just makes sense because we'll draw around 3 amps peak. That's just okay. That worked fine. Maybe we can even increase the trace width. Let's just put it as big as possible. If it routes with 40 mil, we're pretty lucky. Does it do that? It might have some issues. We might have to get at least one trace bar ourselves. Nope, it's not doing it. Let's just cancel that. Also, it's pretty close on the SOIC8 package of the battery charger. Let's put 35 mil, see if that works. If it doesn't work, we'll just go ahead and leave it at 30. That's good enough for our purpose. One failed. Okay, this one failed. Well, let's just put a via here directly on the pad. That will work. Go on the back. Put this ground thing here. Well, that should have fixed it, I guess. Let's just do the net. Yeah, we did all nets. Now we have some clearance problems right here. What's the least important there? Yeah, that's not so important there. Let's just make it smaller. I hope that's the right field. I can't just see it. Let's put it to 30. No, this is something bad I made. I can't see it because there's the screen recorder on top of it. There it is, width. Let's just go here and put 25 in there. That should fix it. Let's see. No design errors, no net errors. The last thing to do would be to put the labels on a nice position. I'm not going to do that now, especially if you get it assembled. It doesn't make too much sense, but then you just go ahead, use area and press left on all the edges where you want to have the copper fill, the copper area, and then you press right in the last edge you had. It will then put the copper pour in there. In this case it's all ground, but because we use a common ground it just makes sense to use copper pour. Let's just make another design rule check and net check. All components are placed as well. You can get most of these parts assembled, and this is your own power bank here right now. Just feel free to build it, use it, send pictures, tell me what to improve and what works and what doesn't work. But as far as I know, I should just do it.